Good afternoon, good morning, ladies and gentlemen, and welcome to the latest EnOcean Alliance webinar. We thank you for taking your valuable time to join us today. Firstly, a couple of housekeeping items. This webinar will be recorded, and we will send the link to all participants after the webinar, also with the presentation materials today. You also have the possibility to ask questions. You can type in your questions during the webinar, and we will address them if we have time at the end of the webinar. If not, we will pass the questions on to the presenters so they have a chance to answer you after the webinar. So today I'm very honored to have three expert and pioneers in energy harvesting join us. Maybe you guys could quickly turn on your cameras, please. So first of all, we have Joerg Hofmann, who is CEO of BSC Computer, who is a promoter of the EnOcean Alliance and has been active in this field for over 20 years. So welcome, Joerg. And then Andi Schneider, also a pioneer, a long-year pioneer in this field for over 25 years in the EnOcean world. So welcome, Andi. And thirdly, we have Roelof Koopmans from Dracula Technologies, who is a pioneer in energy harvesting solar technology. So welcome and thank you also to you, Roelof. Miniature energy harvesting wireless has been pioneered by EnOcean and the EnOcean Alliance over the past 20 years. And the key areas that we have successfully put into volume production have been building automation, smart homes, smart spaces, plus some industrial and transportation, with more than 25 million products being installed over the past 2 decades. Today, energy harvesting wireless, also known by some as Ambient IoT, is beginning to see exponential growth. In the core market of EnOcean, smart buildings, smart spaces, growth is being fueled by government regulations, by compliance regulations, workforce changes, and also the drive to reduce cost and reduce CO2 output. According to industry analyst BSRIA in Great Britain, only 10% of the existing commercial buildings are truly smart. The other 90% are basically dumb. In addition to this, over 90% of the buildings in the EU were built last century or before, and 75% in the United States and the rest of North America. This gives us a huge opportunity for retrofit over the next decades. But energy harvesting is also now becoming a must and very popular in other groups. We're seeing applications such as asset tracking, such as pricing labels, smart appliances, etc., now slowly becoming very popular in energy harvesting. This is also being driven by important groups now acknowledging the necessity for energy harvesting wireless. We cannot pull cables everywhere. We cannot change batteries everywhere. So energy harvesting is being more and more promoted by other groups. For example, in the next 5G specification, Ambient IoT is now part of the spec. Will also be part of the 6G spec. Bluetooth, IEEE are also now acknowledging the necessity for energy harvesting and are putting this in their specifications. And the number of academic papers in this field has increased over the past decade from less than 10 a year to over 500 a year. So we see there's a lot of activity in this. And of course, to meet the demands here, we also have to create better next generation energy harvesters, and that is the theme of our webinar today. Firstly, I'd like to ask Joerg Hofmann and Andi Schneider, to present their research project in silicon linear actuators from BSc Computers. And thereafter, we will go over to Roelof, who will be showing us the low-light organic photovoltaic created and in production with Dracula. So without ado, I'd like to hand over to our first speaker, Joerg Hofmann and Andi Schneider. Thank you.
Yeah. Hello, I'm Joerg Hofmann. I'm the CEO and shareholder of BSc Computer. I give you a short overview about our company. BSc was founded in 1992 by me, and we are a promoter of the EnOcean Alliance since nearly 15 years. We are developing hardware and software with the energy harvesting technology since 2005. But before, we've been a classic IT service provider, and we made a transformation of the classic service provider into a developer of electronics and software. And so I say the first IoT gateway, the name doesn't exist at that time, with EnOcean bringing to IP, we provided in 2007, or in the CeBIT 2009, we provided the first app on a BlackBerry. And so we are over the years always searching and developing new technologies, and especially the energy harvesting technology is our goal. And now we found a new technology. It's based on Dielectric Elastomer Actuators. This is a new technology for harvesting energy, but also using it for linear motion sensoring and other products. So with our network of companies and customers, we always look to develop new applications and implement them into the market. And now our projects are starting with the DEA technology. You can see our business segment is the classic IoT solutions, both based also on EnOcean technology, low power electronics, energy harvesting products are using really low power, need low power solutions. So this is our technology goal, and the dielectric elastomers is a complete new electronic because it's high voltage with special designs, and so now we provide the first products with this. The energy harvesting and the dielectrical technology. Now Andi will show you what is is behind this technology.
Okay, Joerg, thank you very much. By the way, can you all see my screen? I don't have no feedback on that one. I hope so. If not, please give me a feedback. So welcome everybody. Thanks for participating in this webinar. I want to really second Graham in the importance of energy harvesting, getting rid of batteries, and digitizing solutions is really important in order to make buildings and industries smarter and reducing less energy, and by doing that reducing the CO2 output of those solutions. So when we came across those dielectric elastomer actuators, I figured out that, you know, I was always speaking about silicon, and I now need to talk about silicone as well. So silicon is of course the semiconductor side, which I've studied, and lots of people know me being in the low power electronics IoT world for a while. And now we had to learn about silicone, and we start into a lesson. So what are we talking about when we talk about dielectric elastomer actuators? So literally, you might remind from your school lessons some years, decades, months, or whatever ago, that if you have two differently charged plates, those will attract each other. And you might remind the experiment with the balloon, with the Luftballon, rubbing it on your pullover, and then it will stick to the ceiling, for example. So this is exactly the effect we're talking about. And when you put a material between those two plates, which has a certain viscosity, then those plates again will attract each other. And if you build a product like it's now seen on the screen on the right side with capacitor plates and silicone between those plates, and you apply a voltage to those plates, they will attract each other, which makes the whole device shrink. On the other side, of course, you see it looks like a capacitor, and literally it's a capacitor which you can be bended or pressed or so, and then by doing that, changing its electricity characteristics, which you can measure then later on. So we are not inventing this silicone, and we are not inventing those dielectric elastomer stacks. At BSc Computer, we are doing the controls, and we focus a little on the controls. But what is important is that it's not an initiative only from us 15, 20 people at BSc Computer. It is an initiative which is a joint partnership of 3 companies, and there is Momentive Performance Materials, which is doing the raw material, so the silicone, and focusing on making this material in a way that is perfectly usable in this smart material dielectric elastomer actuators. And company Detweiler, which is a Swiss company, which has the competencies in producing rubber parts based on silicones. One important example from them is, all of you might know those Nespresso capsules where you make your coffee. There is a small silicone, is it called Gasket in, so Dichtung in German, which makes the whole stuff working in the steam, which is pressed through this capsule. So this is company Detweiler in Switzerland. They're doing those stacks, putting thousands of layers of conducting and non-conducting silicone above each other to make those stacks work. And last but not least, BSc Computer focusing on the control side of the solution. I will come to energy harvesting a little later, but what is important for energy harvesting is that you build products which require very low amount of energy. And that's literally why this material is so interesting. You can see here this DEA stacks. This picture shows prototypes of stacks which are approximately 20 millimeters, 2 centimeters high. Why silicone rubber? You might think of, I have heard this kind of technology in combination with piezo, but piezo is very stiff material, so it will act only by about 0.2 or 0.3%, whereas we, with those dielectric elastomer actuators, can contract by about 5%, and it's a complete flexible material which makes it very much usable in lots of different applications. I come later to that later on. So coming back to the physics, I said earlier, just apply a voltage on it. Unfortunately, it's not the voltage we have available in an electronic IoT device, which might be a battery, it might be energy harvesting. So it's in the range of about 3 volt input. What we need is unfortunately a little higher voltage, and it goes up to 1000 volt. Actually, we operate the stacks at the moment with 750 volt, and the tendency is that it goes down. But the importance here is, so get a battery powered solution making 1000 volt sounds like a task which is not that easy, and I can tell you there is an easy part because you can do it pretty quickly buying off-the-shelf DC-DC converter. But in order to run a DEA, there is lots more know-how needed because it is not allowed to do a voltage overdrop in the beginning. It's not allowed to have a big ripple. So lots of possibilities to destroy the material if you do it wrong. Our target is to build a module which is easy to integrate and then make those DEA stacks work. In the ideal case, it's a module like, you know, from the EnOcean world, there are those TCMs or STMs. So with defined interfaces, and then there's a connector where you could put those dielectric elastomer actuators and connect them to the controls unit. Actually, we focus on the idea of connecting this material, this new material, directly to the IoT world. Literally, if somebody builds an application where he needs some linear motion, he just can send a command, please act or please sense, give me the value, and then the electronics does everything which is needed in order to either make the device work, so contract, or to get the sensing information. So what is your position? Is it on, you know, is it expanded or is it contracted, or is there an external force on it? So it's bidirectional, which combines the DEA actuation and the DEA sensing stuff. And we also develop some specifics, which is quite used in this world of electronics, so that it automatically calibrates and it automatically compensates if there is, for example, temperature changes in the environment. So there's lots of specialities we will build into these electronics. So now to share with the actual status where we are, right? So we did our first controls unit, and on the left side you see that it moves pretty nicely up from 0 to 720 volt within 1 second. And you also see that there is a very, very low over voltage in the beginning, which is 728 volt, which is the peak. Actually, tick in the box, this is exactly how we need to operate the DEA stack. On the right side, you see this ripple, which is when we are at 720 volts, how much AC we have still on this voltage. And it looks big, but it's only 837 millivolts. So it's a pretty stable DC, which we generate with the controls unit, which is the basis of making the DEA work. Now, the critical stuff I said earlier is now how to make this as energy efficient as possible. And you see here the graphic, what is the evaluation or the development of our product over the last weeks and months. So the orange curve is how we started. You know, the DEA stack, I didn't say that yet, but the DEA stack requires 50 milliwatt seconds in order to operate energy. It's a capacitor, needs to be charged. So 50. If you remember and look at now on this curve, you will figure out that over an activation time of 2.5 seconds, below the orange curve, there's approximately 2,500 milliwatt seconds, so 2.5 watt seconds, which is absolutely not efficient and not make it work. So we focused on really getting that job done and getting the efficiency of our DC-DC converter up. The green one is the second version we did, which was already a 45% energy reduction. And the blue curve is the actual status, where we are in an efficiency of about 40%. So actually, we require now 120 milliwatt seconds into our electronics to make the 50 milliwatt second DEA stack work. And now the interesting thing starts with this, because what we at the end of the day want is what I said earlier. So the IoT say, do something, act, and if there is an external force, get this information back to the IoT. And of course, we want to do that based on EnOcean radio technology with the EnOcean Alliance. And in order to do that, we want to do it battery free, because you know, we don't like battery as EnOcean doesn't like batteries. Actually now, with those 120 milliwatt seconds, which is required to make the DEA act, we are pretty close to run energy harvesting solutions. So for the ones who really love physics, here is the formula. What is the energy needed in order to charge a capacitor? And the DEA stack is a capacitor, which has approximately 150 nanofarad. So in order to make that work and compress by 5%, we require those 48 milliwatt seconds, and those support battery-less energy harvesting solutions. So today we are in a project where we already have the DEA stack in a field trial battery-based in order to get feedback from the market on the operations, on the how does it work over temperature and all that stuff in a friendly customer environment. And we are working heavily on getting the battery of this solution. So what are the energy sources we need here? And Roelof, you will take over afterwards in the next presentation. Of course, you can then build IoT actuators, so with motion inside based on solar, because those energy levels could easily be charged into a gold cap or whatever, and then be consumed out of this intermediate charge in order to make the DEA act. There is other technologies which could bring in energy, like wireless powers, and there are some examples on the right side. I'm pretty sure most of you know those different, and I guess there's lots more which could provide small amount of energy, be stored in a capacitor, and then used and consumed when the actuation is required. What's interesting here is that the energy consumption is now as low as it is usable by or can be powered by NFC. So instead of using your smartphone for payment, you could use your smartphone for open lock. Actually, the concept should be pretty clear for most of you. All the authentication, security, everything is in the smartphone, talks to the backend, and then just transmits some energy plus secure communication to the lock and says open lock. With our DEA, we are able to show actuation within less than 2 seconds of having the smartphone providing energy by NFC to the smart lock. The applications we're working on today is, as I said, the lock. There is where we are in a customer engagement, and we are in the internal field tests at the moment. We are together with Momentive, Dielectric, and BSC. We are jointly developing the next step of industrializing and getting serious products into a lock. The other applications we are working on is on the right side. It's an electronic valve, and from the building industry, you know that there is some requirements for valves which should be noiseless, maintenance-free, and low energy. And with the DEA stack, we support all 3 criteria: noiseless, maintenance-free, and low energy. And the middle is an example of a combination of sensorics plus actuatorics. So there is use cases in robotics, and there are use cases as well in wearables, medical devices, smart gloves, for example. Finally, last but not least, because we're talking about energy harvesting, and now I talked about low power consuming smart material for sensing and acting, which allows energy harvesting. But interesting enough is that the same material, so exactly the DEA stack I showed before, could be used as an energy harvester as well. And like in my first picture, you see here on the right side how it would work. So actually, you would compress the capacitor, the DEA stack, so make it shorter, put some charge on, and then get it back into its original position. And when you do that, there is an amount of energy, electrical energy, which is higher than the amount of electrical energy that you have put in the compressed phase. So literally what this does is it translates kinetic energy into electric energy with a big difference to EnOcean's kinetic harvester, because there is just a movement and then you get energy out in a sufficient way. In our case, we always need to pre-charge, and then we get a higher amount of electrical energy out than we put into the solution. So I recognize that I'm over time already, so I just go to my final slide, which is where's the potential for those DEAs? Actually, there is solutions out there. So DEA are already used in wave energy converters. So that's a huge tubes which are put into the sea, into the ocean, and then create some energy. And we believe that the technology could in future help generate energy out of vibrational motion, or for example, shoes. We are working on that. We are ready for questions later on. And actually, this is an example of new material which could be used for various applications. And I'm very interested in learning from Roelof how his technology can help in the energy harvesting space. Over to you, Roelof.
Thanks, Andi. And also from my side, nice afternoon. Good morning for those who call in from the US. And I have to now see that I get my screen up. So do you see my screen?
Yes.
Okay, good. All right. Okay, all right. So also Graham and the entire EnOcean Alliance team, thank you very much for hosting this interesting webinar. I represent Dracula Technologies, which is a French company, and we are specialized in low light organic PV harvesting, which is the other part of this webinar. And I'd like to show you what the state of the art, state of the industry is in the OPV business. So start off on energy harvesting for those that have not been sort of deeply into this. I mean, I come from 15 years IoT. I did NFC, RFID, and LoRaWAN before I joined Dracula. So I have really an IoT background, and I've run into large IoT projects where the battery got in the way in terms of rolling out and deploying on a large scale. And first of all, there's this process continuity, which is not trivial, because the IoT is all about collecting data, and those data is basically used for applications that will drive business processes within the company, right? So if the sensor goes out of battery, you can imagine that's unacceptable. And in order to do that, companies have to organize staff to avoid that batteries will go down, right? And the sensors keep working. So then we're at the second bullet, which is total cost of ownership. I've seen enterprise clients calculating the amount of effort of staff, how much they need to sort of forecast for, say, the next 10 years to go up the ladder, get the sensor off the ceiling and replace the batteries. It's a huge cost, right? It can kill many business cases up front. Thirdly, it's a regulatory compliance, which becomes more and more relevant, as we all know, coming down from EU, but also the US, more and more green technology is being required. Even in an ocean ecosystem, you see RFPs coming up that actually require battery-free devices. Last but not least, I think we all have also a sense of sustainability, which is, if you think about billions of IoT devices, and if half of those devices, the batteries are being wasted not in a proper way in terms of recycling, it's just unacceptable for having these amounts of batteries just entering up into nature. Graham just mentioned briefly, there's other, I mean, of course, EnOcean was the first, but there's other wireless protocols in the IoT space that are now embracing and adopting energy harvesting into their protocols. So, of course, Bluetooth is also getting into this. We know that a company called Wiliot has RF harvested Bluetooth sensors, which are almost like RFID tags or labels, if you like, that are now making their way into the logistics space. We know that I think the British Royal Mail is using that, and it's kind of a game changer compared to RFID, passive RFID. Then there is other standards like Zigbee that launched Green Power already some years ago. And as Graham mentioned before, Ambient IoT is the credo that 5G or the 3GPP consortium is launching. And it will be in Q3 in the release 19+, there should be an Ambient IoT spec for energy harvested devices, which actually will make those devices much more energy conservative in transmitting data. I mentioned TCO, and I brought a case here that I actually was exposed to with a large IT services company globally. And they actually deployed about 50,000 sensors in about 50 buildings, I think in 15 countries. And I got access to the TCO calculations. And if you look at the total cost of ownership over a 10-year period, which is then the 100%, about 40% was for the hardware, for the IoT sensors. I talk about a LoRaWAN solution here. So there were LoRaWAN gateways and cabling required. There was software required, and there was project management required. So there was about like a bit more than 50% of the total cost of ownership that went into the CapEx, right? The capital expenditure / investment. And of course, sorry, before I forget, the deployment of the entire installation. And the operational expenditure, calculating over 10-year periods, several battery replacements in all those 50 sites for 50,000 sensors is like 25–30% of total cost of ownership, which is a significant part, which is highly underestimated by many enterprises if they go into this IoT kind of solution space. The batteries as such, of course, depending on what batteries, lithium or alkaline or something else, is also a significant portion of the cost. Then is of course the wireless communication cost, connectivity, and this is like 5% for the overall maintenance and support costs. So you can see that the batteries make up for a large part of the total cost of ownership. Now, if you do the benchmark against a organic photovoltaic solution instead of a battery solution, it's going to look like this. We just saw the battery powered solution, which is at the left side, and at the right side you can see the OPV-based solution, which has a much lower operational expenditure cost. So the battery solution would cost over 10 years about 6.5 million euros, whereas the organic PV solution costs 4.5 million. So they're actually going to save 2 million euros if they do the organic PV solution. Now, energy harvesting, I don't think I have to tell, but for those who are not familiar, we are in the light business. My previous speaker, of course, we're in the kinetic business. And then you have also other sources of energy harvesting like thermal energy and RF radio frequency. So within the light harvesting technologies, everybody knows the typical solar cells or photovoltaic cells. They're very common since whatever 40, 50 years. used in pocket calculators and now going on the rooftops of buildings. That's completely different from organic photovoltaic, and I will show you in a minute. Before that, I want to sort of share with you some market research that shows how light will be the main source of energy harvesting for IoT low power devices. Secondly, it will be vibration harvesting or kinetic, and then the other sources, right? So that's an interesting, I think, perspective on the future of energy harvesting in this context. And the other one I want to share with you is what application will gain most of energy harvesting. And it's predicted that smart building, home automation will be the main application, before then in a minor part, industrial, transportation, other applications. So organic photovoltaics, the product that we, Dracula Technologies, are manufacturing, is having some very unique features. First of all, it harvests at very ultra low light, right? I talk about, excuse me. I talk about lux levels that can go beyond 100 lux. Now, in a typical office space, everybody knows is around 500 lux. So talk about 5 lux, it's almost like there's no light at all. And that makes a big difference for many applications, because the robustness of a sensor and the performance is sort of guaranteed at almost dark environments, right? And that's a game changer. The other thing is that we do inkjet printing, the way of we manufacture those modules, which gives us complete flexibility in terms of shape, number of cells, the form, the layer, and the coating, right? So you can just pick whatever design you want, we'll manufacture that. Small series, large series. Thirdly, it's all organic materials. We're not use any rare earths, we don't use any toxic materials. The lifespan, of course, has to be very long, because you don't want to swap modules as you have to swap batteries. So we can guarantee 10 years and beyond. We've done age testing, and we get like at T80, 80% still performance after 10 years in indoor environments. And we produce at industrial scale, where I will show you the new factory that we launched last year. So in terms of the design flexibility, I show you a couple of examples that what we can produce and what we have produced for certain customers. So yeah, anything goes, right? Sky is the limit in terms of shape, in terms of number of cells, how many cells, how they're going to be configured. You see the lower left, which is just an example of something we produced as a gag for some promotion products. And you see in the middle here, different coatings, right? We can do any kind of designs and graphics that fit to your particular sensor design. So the core technology is organic photovoltaic, and we call that layer, which is our trademarked product. And you can see at the right side an animation of how that works in terms of the photons and electrons. And it's based on the 5-stage process, right? Also, the simulation shows those different stages at the right. And it's all about organic materials from carbon, hydrogen. It's being multiple layers that we print on top of each other. Sustainable materials, no rare earth use, and the solvents that we're using are environmentally friendly. So really green technology. For those who have never built an autonomous device, it's not just that you replace a battery with a harvester from Dracula or anybody other's harvester. There's more to it, right? So the way we go with customers is we build a so-called energy brick. The energy brick usually is always inside a sensor that has to communicate wirelessly, whatever protocol you see below here. And you will have to have some storage, because there will be situations where actually there will be completely zero light. So in those situations, you want to sort of store the energy and be sort of able to still have the sensor performing and transmitting data, even in a complete dark situation. So we're using some of our partners, supercaps or micro batteries, but also we launched a product called Layer Volt, which is a combination of energy harvesting and electrical storage on the flip side of the harvester. And I'll talk more about it later. And at the right side, you see the different power management IC options that we typically work with creating those energy bricks, because the PMIC needs to operate and to actually manage the flow of energy between the PCB and the storage, between the harvester and the storage, between the storage and the PCB. So you really need that PMIC in most of the applications. What kind of applications we have been working with our clients? Of course, smart buildings, be that temperature, humidity, or air quality monitoring, or room sensors. This is a mainstream vertical that we're working on, and that's why we just joined the EnOcean Alliance last year. Secondly, smart asset tracking, very interesting, because you don't want to replace batteries in warehouses and logistical centers. And there's a big demand for trackers or cold chain loggers that can actually operate without batteries and hold data for a long time, be that on a container journey across the world or on a truck journey across Europe. So energy harvesting in combination with storage is the way to go. Then we're serving other verticals. You see here electronic shelf labels, ESL. Think about a store which has like 10,000 of ESL labels that will hold for a year or a little longer and then have to be replaced, which is a huge operation for the store to exchange all these ESL labels. So we work with basically all the main ESL manufacturers to bring products to market that can do a batteryless solution. Of course, remote controls and wearables is other applications that we actually work with clients on. I brought 3 examples of customers that we can talk about in public. So one is CoolR, an American company that created a solution to solve a problem that vending machine operators are facing. So the challenge that they have is if they want to do stock taking, this is very labor intensive, right? So if you can automate that with an AI camera that sits inside the fridge, you can save a lot of travel for people to operate those vending machines. So the solution is to connect that AI camera to a cloud application that transmits data either every hour or every day. And the sensor is powered by organic PV from our company, Dracula, which is harvesting ambient light from the surroundings. And it makes the sensor basically completely autonomous. It's quite a big storage element inside this sensor that also makes sure that it's completely dark. It will still work properly, and they have designed this to work 9 months in a complete dark environment. So this is a very robust way to solve this solution. And also the battery, if it would not work because of cold conditions, there's a way to actually work from the harvester, right? So it's a hybrid solution. Then smart labels. There's a Swiss company called Truvami that has created a smart label that can actually log data on the journey through logistical operations in warehouses or industrial applications, and can provide geolocation data outside as well as inside. So that's a real game changer. And this is done without batteries, right? So with this label you see here, you can get a location, but even temperature and other condition data wirelessly communicated through a LoRaWAN network that communicates with the cloud application of the client and actually provides full visibility on the assets that are carrying such a smart label. This is actually like, you could say, RFID 2.0, because it just brings real-time location tracking up to a new level, completely passively, completely autonomously. And this is like, as Graham said, this is ambient IoT. In the smart building space, we have a customer called Orioma, a French company that has created ceiling-based presence detection, PIR sensors. And the challenge here, of course, is how can we avoid that people have to climb a ladder to change the batteries, right? That was the main challenge, and that's how they came to us. And this is a LoRaWAN sensor communicating wirelessly. And the smart thing they did here is they created a 360-degree angle, so it's actually catching light from any direction. And since we are as flexible as it has to be to produce such a flexible OPV module, you can see in the lower left that we just produce like half circles that you can fit together as a cone. which goes into those sensors. Now, light is not something that's pretty stable in an environment like an office space. You see here a snapshot of light intensities. So at the window, you will get like 3,400 something lux. But if you look under the desk, you only have like 13 lux. So there's a huge variety in light intensities inside a room, which you would never guess, which actually requires a sensor that, for example, a desk sensor that sits underneath a desk to detect where the people are working at a desk, has to be able to harvest light from only 13 lux, right? That's where we're coming from. It makes solutions very robust because you don't have to worry too much about will there be enough light, which many customers are asking us, and we show them that this is possible, right? It's a game changer. This is to give you quickly a feel for how much electrical performance you can expect from different modules. The module I show at the right side here is like 6 by 6 centimeters. And if you look at, say, 1,000 lux, the lower row, you see at the most right column, the power max, you get like 1,025 microwatts out of this module, which is about like 1 milliwatt, which for most low power devices is enough to have a proper designed PCB. As I said before, we opened up a new factory in France to deal with all the large demands that we're getting for producing millions of OPV modules, and I'd like to sort of give you the gist. Yeah, so I thought I'd show you this because some of our prospects and customers say, hey, inkjet printing, that sounds like easy, right? So no, this is high tech, this is clean room manufacturing to get to this kind of high performing organic PV modules. And it took us like more than 10 years to get here, right? So we're well funded by several tech companies as well as financial institutions. And we invested at least 10 million euros just in the R&D to get to a product that can be manufactured on large scale, high performing, low cost. And this factory is ready to manufacture at least 150 million square centimeters a year at one shift. And if we go to 3 shifts, we're close to 500 million square centimeters a year that we can manufacture. So we're ready to roll. We have a team of more than 40 people working in Valence, which is the southern part of France. And we got like 29 patents granted or pending. So before I close, I want to show you this latest product that we launched last year. We got a couple of awards, the CES and other big shows for this game-changing innovation, which is, as I said already earlier, it's combining at the front side the energy harvesting module, organic PV, and having a storage, printer storage at the back, at the flip side of this thin film flexible product, right? So it gives basically almost a complete solution, replacement solution for any batteries that go into sensors, and you can shape them in any form. So with that, I'd like to close here and open up for questions. Thank you very much for having attended.
Yeah, thank you very much, Roelof, and also thank you to Joerg and Andi for these excellent presentations on this great innovation. We've actually run out of time to take questions. We're a little bit over time, but I will pass on the questions that any of you have put in to the presenters. Or please feel free to contact myself or the presenters directly with your questions or comments or interest in these new innovations. And again, I thank everybody for participating. I thank our speakers, and I thank Mickey, who has done all the background work here. And we look forward to seeing you all in our next webinar. So with that, thank you all very much indeed. Have a great evening. Have a great day. Thank you very much. Bye-bye.
Thank you. Bye.
Thanks. Bye-bye.